Hi, my name is David Keller, and as introduced by Jerry Bennett, with my colleague Andres Amaya-Garcia, I've developed the OpenTransputer as our final year dissertation at the University of Bristol. So the OpenTransputer is a microprocessor based on the Transputer architecture. Transputer was developed in the 1980s by Inmos. And when I use the word architecture in this presentation, what I'm referring to is the interface between a programmer and the hardware, or the interface between a compiler writer and the hardware, whereas the term microarchitecture refers to the internals of the hardware and how it actually executes the program. And as a compiler writer or programmer, you never directly interact with the microarchitecture, but I'm sure most people here are familiar with that distinction. So when the Transputer was introduced in the 1980s, it was not just revolutionary for its on-chip memory and on-chip communication links, it also introduced a completely new paradigm of how to build systems. So much like a transistor can be thought of as a building block to build processors, the Transputer and the OpenTransputer are building blocks to build any kind of system at a much higher level than we're used to. And this facilitates integration and designing systems. This also meant the Transputer found its way in all sorts of applications, including spacecraft, satellites, set-top boxes, and supercomputers. So the question you might ask yourselves now is, why did we think it would be a good idea to re-implement the Transputer? Because while it was clearly successful, it is also not around anymore. So what we've seen in recent years is the trend of the Internet of Things, a developing, emerging market. The Internet of Things is the idea of a world where every device is connected to every other device. And this market requires a small, power-efficient microprocessor that has easy-to-use communication and concurrency primitives. So while we not necessarily expect the Transputer to find its way, or the OpenTransputer to find its way into your tablet or mobile phone, or even the data centers in the cloud, it would be in all the other devices that make up the Internet of Things. So what we've achieved during our dissertation is we've developed a new microprocessor based on the Transputer architecture that uses state-of-the-art technology. We've also replaced the communication mechanism of the original Transputer with a more scalable one, and we introduced a new I/O interface that makes interfacing with I/O peripherals much easier. So how does it all work? So any good presentation on the Transputer will start with an introduction to OCaml, and this presentation is no exception to it. So OCaml is a high-level programming language that was developed hand-in-hand with the Transputer at Inmos. And what makes it special is that it has special primitives for concurrency and communication. One important notion in OCaml is the idea of a process. So whereas in a procedural programming language, a language like C, programs are made up of procedures, callable blocks of code, OCaml programs consist of processes. And a process is an independent entity with its own state and memory. And at the bottom of this slide, we see three simple processes. We have an assignment process, a channel output, and a channel input process. And on this slide, at the bottom left here, you have a simple sequential program that first is a channel input, then reads from a channel into the variable y, and then assigns the value of y to a variable z. So this would be the sequential program flow that we can see over here. On the right-hand side, we have slightly modified this program, and in this indented part block means the channel input and the channel output happen in parallel, which can be seen in the program flow above. So when the Transputer was released, it essentially came with its own real-time operating system implemented in hardware. And so it had a scheduler implemented in hardware. As we can see here, multiple processes can be run or queued to be run on one processor. Here we have process X, Y, and Z. Each of them has what is called in OCAM or the Transputer world a workspace. A workspace is a location in memory where the context is stored, and the running process Z also has access to a set of registers. A, B, C, they form an evaluation stack, a workspace pointer, an operand, and an instruction pointer. The other processes that are queued are scheduled to be run, and this scheduler is implemented as a linked list in hardware. So special instructions in the Transputer implement all these OCAM primitives we have seen, including the scheduling and also the communication. With regard to communication, one has to differentiate between off-chip and on-chip communication. On-chip communication is performed by a word in memory. Off-chip communication is done via the physical links of the Transputer. And behind all that OCAM is, of course, the OpenTransputer. So the OpenTransputer can be thought of as a system of three parts. There's the main CPU, the external communication mechanism, and the I/O interface. So I want to start by talking about the CPU in a bit more detail. So again, the CPU can be subdivided into three different units. There's a fetch unit, which fetches the next instruction for memory. The data path, which is made up of modules like the register file or the ALU. And there's a control unit, which at every clock cycle generates signals that control the operation of all the other modules in the CPU. So let's have a closer look at the control unit. In general, there's two ways of implementing a control unit. A microcoded approach or hardwired logic. So in a microcoded approach, the controls in each assembly instruction is executed by a sequence of hardware implemented micro instructions that are essentially, they refer to a set of control signals. In the original Transputer, these micro instructions were stored and loaded from a microcode ROM, a read-only memory. This resulted in area savings and also meant that it could be modified in later stages of the development. In the OpenTransputer, we developed the control unit with a hybrid approach. We designed it with a microcoded approach, but the actual control unit logic is implemented by hardwired logic. Hardwired logic means we use actual blocks of logic to generate the control signals at each clock cycle. And so this means we get the best of both worlds. We can modify them relatively easily, but we also get potential performance benefits because we don't have to keep reading from memory to get the control signals. To do this, we developed our own MicroAssembly language, which is essentially a human-readable format of the microcodes and the micro-instructions. And then we wrote our own tools to take these MicroAssembly instructions and translate them into actual Verilog HDL. And here's such an example of a micro-instruction, or two micro-instructions rather. They implement a conditional jump. And what we do here, we compare the constant 0 to A, and then if they're the same, so if A is 0, then we jump to CJ2, which is not displayed here. Otherwise, we jump to CJ1. And in CJ1, we pop the stack, clear the O register, and then increment the instruction pointer by 1. Let's have a look at the data path of the OpenTransputer. So, let's start this by first talking about the original Transputer. Back in the 1980s, when developing a processor, there was quite a lot of constraints on the manufacturing process. This meant you could only have a limited number of wires, because it was difficult to have wires crossing over each other, and you could only have a certain limited number of limited amount of interconnect. This is why the Transputer used a shared bus system as displayed here. So we can see two operand buses which carry values from the registers to the functional units, and a result bus at the bottom which carries the output of the functional units back to the registers. Also, with the OpenTransputer, we didn't have the same sort of constraints when implementing the data path, which means we have a much wider data path. In this data path, every register is connected to each functional unit by an individual wire if that functional unit needs a value from that register at any point. So this means we can exploit a lot more parallelism within when we execute each instruction, because different functional units can be fed different values at the same time. And for the same reason, we also have multiple instances of certain functional units. For example, the OpenTransputer has 3 address units, which further helps us exploit that parallelism within each instruction. Let's have a look at the external communication mechanism of the OpenTransputer. So the original Transputer had 4 serial communication links, which meant you could build transputer networks in a point-to-point fashion that look sort of like this network here. We thought this approach reduces the usability of the Transputer as a building block for large parallel networks, which is why we replaced the 4 bidirectional links of the Transputer with a single bidirectional link that connects it to a network of switches. Because the problem with the point-to-point approach here is that as networks grow large, it is very hard, and communication might have to be relayed of an increasing number of processors, and limits the scalability. The network that we use here is a network of switches that are connected in a Bennis fashion. Bennis networks are used in telecommunication systems as well, and they allow for rearrangeably non-blocking communication. We also introduced the notion of virtual channels. So in the original Transputer, only 4 processes could be performing external communication at the same time. In the OpenTransputer, you can have an arbitrary number of processes waiting for external communication. We also increased the number of input ports from 4 to 16, and we have a single output port. The I/O interface is completely new and was also developed as part of the OpenTransputer. So the I/O pins, we have 15 of them, are treated as like any other channel. So to set a pin high or low, all you have to do is send a 1 through a channel, or to set it low, you send a 0 through the channel. We also introduced a new assembly instruction, conf.io, that changes the pin from an output to an input or back. At this point, I will show you a demo. I've got the video of the demo, and I quickly want to talk to you about what we can see in the demo. So it runs off an FPGA, and there's 2 Transputers that are connected by a switch. One of them is connected to a motion sensor, which will then send a signal to the other one if motion has been detected. And the other Transputer is connected to LEDs, which will then flicker in a certain pattern if a motion has been detected. And I've got a video of the thing here. So as we can see, these LEDs are flickering. The motion sensor is right here at the bottom. And if the motion stopped, the pattern would be static. I'm not sure if you were able to see this. Maybe I'll just play it again for. So as we can see, there's a motion. Now it's static. And now we're waving our hand, which unfortunately you can't see on the bottom here. And that's our little demo. This is the code we used to run the demo. on the processor that is connected to the proximity sensor, we simply receive a value from a channel into the flag moved, and then we send this flag through channel 0 to the other processor. The other processor is connected to 8 LEDs, and depending on the value of the moved flag, the LEDs are updated to flash in a certain pattern. So how well did we do our design? So we synthesized the OpenTransputer for both a set-board FPGA and an actual 180 nanometer manufacturing process. And in terms of performance, what we can observe in the first row here is that the simple load instruction has improved by a factor of 2 going from the Transputer to the OpenTransputer. And this is in general the case with all primary and secondary instructions in the Transputer. And this can be explained by the added parallelism to the microarchitecture as I was talking about earlier. And the start P and end P instructions are responsible for scheduling and descheduling processes, and we can also see an improvement by a factor of 2 to 4 here. The explanation for this is that we've introduced the notion of shadow registers. So in the original Transputer, when switching from a high priority to a low priority process, context would have to be stored in memory. And we introduced new registers, shadow registers, where this context is stored, so we don't have to access memory. And with the move instruction, we can actually see a performance degradation, and this is simply because we haven't optimized this part of the design yet. There's also an interesting observation to be made regarding Moore's law. So the original Transputer was manufactured in a 1 micron or 1000 nanometer process, as we can see here in the table. So by scaling this down to 180 nanometers, we have improved the manufacturing process by a factor of 5.6. Now, if we assume that the OpenTransputer was the exact same processor as the original Transputer, meaning it would have the same number of transistors, we should also see an improvement in the area by a factor of 5.6 squared. The actual improvement is 4.2 squared, and this difference can simply be explained by our design, which is more complex than the original Transputer, and also by the lack of optimizations. It does give us a good indication, however, that we developed a new microprocessor based on the Transputer architecture. We replaced the original microcode ROM with hardwired logic. We also modified the data path to exploit more parallelism within each instruction, and we added a new communication mechanism and a new I/O interface to make it fit for tasks that we have in the year 2015 and in the future. Thank you very much. Any questions?
So in your switching framework to route things between processes, it's a binary tree hierarchy, right?
It is recursive, yes.
So how do you avoid starvation in the switch architecture? For example, if one processor tries to send a lot of data quite far across the switch, you need to traverse to the root and back, and that blocks other processors traversing the same path.
Oh, so as I said, this network is rearrangeably non-blocking. You're right, if you assume this is our network, you might have to traverse to the third layer here and then send a message, for example, to this processor. So yes, what rearrangeably non-blocking means is we can always find a path through the network from an input to an unused output without overlapping with any existing communication.
Okay.
Does this answer your question?
So you need to centrally control the path through the switch to do that, right?
Oh yeah, so at the moment the allocation of communication is static, so we assume you know what your communication pattern looks like.
Thank you.
Rearrangeably in this context means so you might have to move existing communication, but non-blocking means you can always achieve it in such a way then there's no overlap between processes.
Thank you.
David, where can we get the Verilog to play with this?
So we'll be releasing the open source code to the processor soon, hopefully. It depends on, so we are currently investigating several ways of how to finish design. At the moment it's a very early prototype, so I mean the idea is to release the open source code eventually.
I encourage you to do that early because you might find people help you finish it off.
Oh yeah, if anyone is interested and has ideas how what we can do with this, please come and talk to me or send me an email on OpenTransputer.org.
John?
You have a list of kind of micro-ops that you somehow compile into Verilog, right? Those aren't one per cycle, I guess. How do you decide where to draw cycle boundaries, or do they all happen in one cycle?
Oh, I think they do happen all within one cycle. We will show that.
Did you write an Open compiler to read in a high-level language?
No, we use the original Open compiler, which is still maintained by the University of Kent.
Is that compiler open source?
It's open source compiler.
Yeah, the open, all the CMOS tools were open sourced in like 1995. I took the precaution of doing that before they disappeared inside the company. Amusingly, part of the motivation for this project was I suddenly realised about 3 or 4 years ago that all the patents have expired. So there's absolutely no hold anybody has on this architecture anymore. Anybody can use it.
Andy?
So on that similar subject, have you seen the XMOS processor and how do you compare?
Oh, yeah. So I've actually used an XMOS processor as part of my degree at the University of Bristol, and the architectures are quite similar. So I mean, the XMOS uses quite a few of the ideas that made the Transputer what it is. The main difference, I'd say, is the XMOS processor is a register architecture, whereas the Transputer and the OpenTransputer is a stack machine. So what this means, like in practice, it is very easy to scale a OCaml program from one processor, one Transputer, or one OpenTransputer to 1,000 without any additional modifications to the hardware, or scale it down from 1,000 OpenTransputers back to one. Whereas with the XMOS architecture, you might have to do some fiddling if you want to go that large. So it's definitely possible, but you have to modify the software to make that happen.
What sort of dev board FPGA-wise are we going to need when you open source the HDL? Is it going to be a very specific board, or do you think it's going to be able to run on over anything?
So currently we use Vivado and a set board FPGA, as I said. So I mean, the Verilog code will probably just work in a simulator without much fiddling. To actually get it work on a specific FPGA, I think there's always some custom stuff that you might have to do. Hopefully we have like some sort of community that can help out with that.
Leading on from that, do you know how many LUTs and what other resources of the FPGA, what sort of utilisation are you getting for different components?
Yeah, we did make we did analyze that part quite a bit in our dissertation. I think about 35% of the FPGA is utilized by the design, by the demo that I showed in the video.
So that's 35%, and it was a
Set board, sync. Yeah, that one. I'll upload the slides and we can have a chat about this later.
What kind of clock speeds do you get? And do you have any thoughts about how to reduce the cycle time?
Do you mean clock speed in the FPGA?
Yeah, the processor.
Or the processor. So like with the FPGA we get about 42 megahertz of the set board. With the actual manufacturing process we haven't fiddled around with that much. I mean if you did optimize it, and then we hope we could get up to maybe 200 megahertz. That would be the sort of range we're aiming for.
Would you be able to pipeline that or kind of increase the clock speed somehow, or that would be difficult?
I'm not sure if the Transputer architecture is very good at being pipelined because it's a stack machine. I think ST Microelectronics actually did try that with later generations of the Transputer, but I think it goes a bit against the the Transputer, the idea of what a Transputer is. Yeah, we haven't experimented with this for the OpenTransputer.
There were actually some pretty fast Transputer implementations done in the 1990s. But it is a slightly tricky one to do because of the stack, the register stack, which essentially makes every instruction to some extent dependent on the previous one. And that's one of the disadvantages of the stack architecture. On the other hand, it would be quite interesting to know more about the performance here because it is actually a very simple processor. Synthesized to anything like a state-of-the-art processor, like anything else, it would be limited by the memory speed almost certainly. So there's an experiment for somebody to do.
So you mentioned that one of the benefits of your design is that you improve process switch time by using shadow registers. Is there a limit to the number of sets of shadow registers you can have, or what do you do when you hit that?
I mean, theoretically, you can have as many registers as you like. I think at the moment we keep it quite low. I'm not quite sure how many sets there are, but I think there's only one at the moment.
Actually, I can help with that. He's actually referring to the registers that result from the fact that the Transputer actually has two priority levels. It's had a high priority and a low priority. And the switch originally between high and low priority was done by dumping registers into memory, reloading from there. What they've done is to eliminate that overhead. Okay, so that means that the worst case performance of these instructions is dramatically reduced. They also actually have an improvement on the cycle count of a number of these instructions, which arises purely from the fact they've got more paths. So they can actually do more things at once within each of the scheduling instructions. So there's actually two contributory factors here. It was quite interesting. I never realised in the original Transputer design that we had been constrained to a significant extent in the way the microcoding of the scheduler was done. Because you can now move more data around at a time, it takes fewer microsteps for each of the scheduling instructions. So we've actually got a gain in efficiency there as well. So the scheduler is even faster than the original.
David, thank you very much indeed.
Thank you.